Hello there, Mr. Sutton bringing you a lesson on solids. We'll be introducing these concepts to you here. So we'll be identifying and classifying solids with multiple representations. And for the real-life application, well, we do live in a 3D world, so this is important. Let's start with some important definitions. A solid is just any three-dimensional figure. Now, some of these are pointy and some of them are curved. The pointy ones are called polyhedra or polyhedron singular. This is just any figure whose faces are polygons. So here's an example of one of these. And by the way, faces, we're talking about the polygons themselves that are on the solid. So, for example, this square up here is a face. We can also talk about the edges of a polyhedron. That's the intersection of two faces, like this right here, this line. And we can talk about the vertices, or vertex singular. That's the intersection of three faces. So, for example, this point down here where all three of these faces meet. Now, there's a unique relationship between the faces, edges, and vertices of any polyhedron. It turns out that the number of faces, F, plus the number of vertices, V, is equal to the number of edges, E, plus 2, all the time. And this is called Euler's theorem. We're not going to prove Euler's theorem, but we're at least going to demonstrate that it works based on this figure here. So how many faces does this figure have? Well, we've got the top, the bottom, and the four sides, so that's 6 overall. For vertices, you've got the 4 points up here and the 4 points down here on this rectangle, a total of 8. For edges, you have the 4 sides of the square on the top, the 4 sides of this rectangle on the bottom, plus the 4 lines here that are connecting the two shapes. That's a total of 12 edges. And 6 plus 8, that's 14. That's going to be equal to 12 plus 2. Oh yeah, so Euler's theorem does work. Awesome. Euler's theorem is so awesome that we're going to take a moment to test it out. So let's say we have a polyhedron with 9 faces and 21 edges. How many vertices does it have? One way you could do this is try drawing the thing and counting the number of vertices, but that takes a while, especially, 21 edges, that's just weird. So instead, how about we write Euler's theorem out, plug in the stuff we know, and solve for the stuff we don't know. What do we know? We've got 9 faces, so that's F, 21 edges, so that's E, so we can say 9 plus V equals 21 plus 2. 21 plus 2 is 23, minus the 9, that gives us 14 vertices. Really quick, don't even have to draw the thing. All right, pause the video and try out the next one. So again, Euler's theorem, we've got 6 faces, so that's F is 6. V is going to be 7. We're looking for edges, so we'll leave E there. So we've got 13 minus the 2 gives us 11 edges. At this point, we're going to start classifying polyhedra. To do that, we need to take a look at 3 broad classes of polyhedra first. The first big class is these guys here. These are called platonic solids, or regular polyhedra. These all have the characteristic that all of the faces are regular and congruent. So for example, these are all the same polygon, these are all the same pentagon on this one shape, and every single side on here, every single edge, every single angle, they're all the same. So these are really good for using for dice so that you have an equal chance of landing on each side. Now another class are these ones here called prisms. These have 2 parallel bases, and bases don't necessarily need to be on the bottom or the top of the shape. They could be on the sides, like here, this pentagonal prism. It's basically just whatever the sides are that are parallel. And this becomes confusing when you're talking about these rectangular ones where, we have lots of different parallel sides. So we don't really know until they tell us what the bases are on a rectangular prism. Another characteristic is that the non-base faces, the lateral faces, are all going to be rectangles on prisms. And then that leaves us with our last polyhedra, the pyramids. These all have a single base and the triangular lateral faces you see here. So they all have these triangles meeting at a common vertex. Let's talk briefly about naming prisms and pyramids. It's all about the base, and it really is. We always name these 2 kinds of shapes based on their base shapes. So this first one, first off, is it a prism or a pyramid? Well, we've got 2 parallel bases, so that's a prism, and since the bases are pentagons, that means this is a pentagonal prism. Go ahead and see if you can name this next shape. All right, so clearly this is a pyramid. We have these triangular faces and a single base. And what is the base shape here? Well, we have a pair of sides across from each other that are congruent and another pair that are congruent, but we don't know that all four sides are the same. So at best we can say that this is perhaps we have this right angle in here, so this is a rectangular pyramid. So we've been spending a lot of time talking about polyhedra, but now it's time to give the non-polyhedra some love here. These are the curved solids. So for example, a sphere. This donut shape here is called a torus. We also have a cylinder and a cone. It's kind of the curved version of the pyramid. Now that we've seen all the types of solids that are out there, let's look at another way of representing them, the net. A net is just an unfolded diagram of a solid showing all the bases and faces. And these are really good for visualizing surface area. So for example, this cylinder could be represented as follows, a cylinder net. We've got these two circles here to represent the bases. And if we were to unfold this lateral surface area, that would just be this rectangular piece. So based on this idea, here are three other nets of different shapes. Pause the video and see if you can figure out what the original solid was for each of these. Now the way I use to figure these out, I look at the bases or try to figure out what the base shape is and how many of them there are. For example, here I know this is a curved piece, so it's not going to be one of my polyhedra. We've got a single circular base, so this is most likely going to be a cone. And if you fold this together, this is the pointy part at the top here. This next piece, we've got these two triangular pieces, but there's these three rectangular faces as well. So with all these rectangles, this is most likely going to be a prism, and these are going to be the two triangular bases. So we could call this one a triangular prism. And this last one, we have these triangular pieces. There's four of them, so these are going to be the lateral faces, and they're all getting folded up around this single square or perhaps rectangular base. So we could call this one a rectangular pyramid. If we knew that these sides were all the same, we could also call this a square pyramid, but they didn't put that in the diagram. Let's talk briefly about the difference between convex and concave polyhedra. Concave polyhedra have caves or indents in them. Convex ones don't. So pause the video quickly and see if you can figure out which one is convex and which one is concave. All right, this first one doesn't have any indents or caves, so this is convex. This one has a cave right here, so that's going to be concave. Hey, pretty easy, right? Let's talk about cross sections. A cross section is just the shape of the intersection of a plane and a solid. So for example, if we have this pyramid and this plane intersecting it, the place where those shapes intersect, this two-dimensional triangle here, this is our cross section. So with that idea, pause the video and see if you can describe the shape formed by the intersection of the plane and this cube here. All right, so for this first one, it's very important. They told us that this is a cube. That means that if we have a cross section here that's running parallel to the bases, this is going to have to be a square. If you take a cross section of a cube this way, you definitely get a square. All of these sides are the same, all the angles are the same. Over here, we're taking kind of this diagonal 3D cross section. So what is this shape formed in purple here? Well, this is going to be a trapezoid. It looks kind of three-dimensional here, like we have a little point coming up from the purple, but that is just because of where the purple trapezoid is. Keep in mind, cross sections are always two-dimensional. So that's it for this one. Hopefully by now you have a solid understanding of three-dimensional shapes. Until next time, this is Mr. Sutton signing off.